Okay, so pressing forward, we set this up in the last video, which is if delta G standard is less than 0, then K is greater than 1. Then we have a favorable reaction, aka exothermic, and delta G standard is larger than 0, then K is less than 1, and you have an unfavorable reaction. Also, you can work it in this way where if K is bigger than 1, then delta G standard is going to be less than 0, and if K is smaller than 1, then delta G standard will be bigger than 0. And in both cases, favorable and unfavorable reactions will result. So in this video, I want to tie delta G to entropy. We mentioned that before, that we said in biological systems that any physical or chemical reaction, if a process has a delta G less than 0, this process happening will increase entropy. If the delta G is larger than 0, then it will decrease entropy. So we're going to use our example of diffusion, put in delta G into a 2. So let's look at our example of diffusion. So we had our two solutions that are separated by semi-permeable membrane, and we had 3 states. So here's our compartment, semi-permeable membrane, state 1, state 2, alright, okay. So here's our solute that can cross the semi-permeable membrane. So in one instance, everything was on the left-hand side. And the other extreme, everything was in the right-hand side. And in the middle, evenly distributed on either side. And we gave these compartments a name. So A, B, A, B, A, B, right? Okay, so we're good. So let us now tie this to delta G. Now we're going to draw out our reaction progress diagram. Okay, so we have this state. This is obviously a high energy state right here. This is obviously a high energy state right here. And this has to be a lower energy state because we know that in the case of, and we'll number these states just to make our life a little bit easier. So we'll call this state 1, state 2, and state 3. So we know state 1 is a high energy state because it will spontaneously move to state 2. We know that that will happen. Diffusion will happen and things will want to be evenly distributed. Solute would like to be evenly distributed. So from this direction, you're going to have a delta G for this. So here's our delta G. And this is from going from state 1 to 2. And this will be less than 0, right? And now for this, going from state 2 to 3, we have a delta G2 that will be greater than 0. And this is from going from state 2 to 3. But we know that the absolute value of the two delta G's are equivalent to each other. Delta G 1 to 2, its absolute value will equal to the absolute value of delta G 2 to 3. Meaning that the number is the same, the sign is different. In the case of delta G 2 to 3, it will be a positive number. In the case of delta G 1 to 2, it will be a negative number. Now, by just looking at this picture, you guys know that this is a state of the highest disorder, right? So this is max entropy. And this state and this state are minimum entropy. It's the most organized. Forgot my R. There we go, entropy. There you go. So this state right down here, state 2, the bottom, right here, pointing arrows to it, all right. That is the maximum state of disorder that this system can achieve. It cannot go any lower. If the system moves in either direction, meaning you go, so let me go ahead and get rid of this stuff so this doesn't get too busy. If the system tries to move in this direction or this direction, in both cases, it is ordering itself. So you will have a positive delta G, right? So you might be saying, but you just told me delta G 1 to 2 is less than 0 and it's favorable. But now we're moving in the opposite direction. We're not going 1 to 2, we're going 2 to 1. So delta G of 2 to 1 will equal to negative delta G 1 to 2. In this case, since delta G 1 to 2 is a negative number, delta G 2 to 1 will be a positive number. And we already know that delta G 2 to 3 is bigger than 0. So this going in the direction of from 2 to 3 is not favored. So in the case of a chemical reaction, it's a little bit different, but it's the same. And the difference is this. So let's say that I have a reaction A goes to B. This is a chemical reaction. It has a delta G standard, and let's say this is a favorable reaction, meaning that it has a delta G standard less than 0. Let's give its equilibrium constant a number, because we're just doing an example. So let's say the equilibrium constant is 10. It's a favorable reaction. The equilibrium constant should be bigger than 1, and you can actually calculate the delta G standard from K equaling to 10. That's not a problem. It'll be negative 5.9 kilojoules per mole. So here we have our reaction progress diagram. Again, the y-axis is energy, and the x-axis is reaction progress. Let's say our starting state is when concentration of A equals to B. So concentration of B divided by concentration of A equals to 1. What is this bottom part? We'll say the bottom part is when concentration of B, the product, over A equals to 10, which is the equilibrium constant, right? So we went from, or we can just say 10 over 1 just to make the point, but it's still 10, right? So what will happen if we keep making product, if we attempt to keep making product? We've reached this bottom right here, but we attempt to keep making product. Well, if you try to keep making product, what you're going to do is you're going to go back up here. Let's say that we're trying to get to B over A equals to 100 over 1. Now, the energy level differences here, I kind of drawn them to be equivalent to each other, but that's not necessarily true. So don't take these levels to be actually super accurate right now. I'm just trying to, through a diagram, explain what you guys will be calculating in the next part, okay? So here I have a delta G for this process. And we know this delta G is less than 0. And then we have a delta G for this part. And we'll call it delta G prime, which is bigger than 0. So why is it that this right here is the bottom? In the case of diffusion, it's very easy to see. Well, you have maximum disorder when you have equivalent amount of the solute in both compartments. That just makes sense, right? But in the case of chemical reaction, I'm telling you that a ratio of 10 to 1 is the lowest state. This is the state of maximum entropy. If I move in any direction, whether it is going this way or that way, I am ordering the system. Thus, it will have a positive delta G, and it will not happen spontaneously. Whereas, going in the opposite direction, this is disordering the system. Therefore, it will happen spontaneously, and it will have a negative delta G. The thing to get beyond, to really start to kind of get a grasp on it, on this topic, is that in the case of chemical reactions, equilibrium, which is being shown in this red box, that state is a state of maximum entropy, and you're not going to have equivalent amounts of reactant and product. You'll have some ratio. In this case, this is a favorable reaction, so you have more product than reactant at equilibrium. And it's a ratio of 10 to 1 in this case. It could be 1,000 to 1, or if it's an unfavorable reaction, equilibrium could be 1 over 100, 1 over 1,000, or 1 over some other number, right? Some number less than 1. So, but that is the state of maximum disorder. And that's just the way it is. Why it is the state of maximum disorder, that is well beyond this class, and it requires learning a lot of physics, and I'm not going to pretend that I completely understand it. I just know this is the case. Alright guys, next video we're going to actually calculate an example, or at least go through an example. Okay, I will talk to you guys soon. Bye bye.